Looking out the window, you see the tangled branches of trees, which seem to grow randomly and irregularly. Sudden gusts of wind shake the branches, causing leaves to fall unpredictably. Our world is filled with these irregular shapes and phenomena, but, as the saying goes, there is order in chaos. What seems chaotic and disordered is actually governed by very simple rules. This concept is known as fractal theory. Would you believe me if I told you that the order of the universe is hidden in this tiny broccoli? Today, we're going to talk about fractals, the basic structures of nature that create complex phenomena from simple rules. Those familiar with computer graphics or fluid dynamics know that simulating ocean waves requires immense calculations. The same goes for weather forecasting. Even with supercomputers, predicting long-term climate or sudden changes is extremely difficult. In science, this complexity of nature is called chaos. In the 17th century, with the establishment of Newtonian mechanics, scientists were confident they could predict all natural phenomena around them, but in practice, it wasn't so. Chaos, as its name suggests, was too confusing and seemed disorderly. However, scientists did not agree that the world was disordered. They couldn't accept it. They believed that our interpretation abilities were lacking, not that the world was chaotic. Over time, curiosity about the laws of the world was reignited by a meteorologist. In 1961, American meteorologist Edward Lorenz made a surprising discovery. A very simple equation he created to simulate weather patterns produced extremely irregular and complex results under certain conditions. This meant that even a simple rule, when repeated, could result in very complex outcomes. This was a paradigm shift for scientists. They thought complex equations and methods were necessary to interpret the chaotic natural world. But they realized that perhaps very simple equations and laws could also handle the complex phenomena of the world. Here's a shape called the Sierpinski triangle. It looks very complex, but drawing it is very simple. Start with an equilateral triangle, draw a triangle connecting the midpoints of each side, and remove it. You get 3 smaller triangles. Repeat the process with each of the 3 triangles. If you keep repeating this process infinitely, you get this complex shape. From a very simple, repetitive process, you get such a complex shape. Let's look at another example, the Koch snowflake. It also looks complex, but has simple rules. Start with an equilateral triangle. Divide each side into 3 parts, and add a triangle in the middle. Repeat this process infinitely, and you get the Koch snowflake. Isn't it fascinating? The common feature of these shapes is that very simple rules can create very complex forms, and this results in self-similarity. What is self-similarity? It means that the parts resemble the whole, and the whole resembles the parts. If you zoom in on a part of the shape, you see the same shape again. Even if you zoom in infinitely, the same shape reappears. This is self-similarity, and structures with this self-similarity are called fractal structures. The most significant feature of fractals is, as mentioned, that part equals whole, and whole equals part, repeats and cycles. But there is another incredible characteristic that results from this. The total area of the shape is finite, but the total length is infinite. What does this mean? If you draw a Sierpinski triangle on paper, you only need one piece of paper because the size of the largest triangle is fixed. However, you would need an infinite amount of ink to draw the triangles because you keep repeating the process of drawing triangles within triangles. Mathematically, you need an infinite amount of ink. Fractal structures commonly have a finite area, but an infinite total length. Isn't it amazing that finite areas can result in infinite lengths? In 1967, a paper was published in Science. It asked, what is the total length of the British coastline? Polish mathematician Benoit Mandelbrot said that the length varies depending on the measuring unit, and that if measured with a very small unit like an atom, the length becomes infinite. Mandelbrot named these structures fractal, from the Latin word fractus, meaning broken. Scientists found fractal structures everywhere in nature. Look at broccoli. If you break off a piece, it looks like a small broccoli, and if you break that piece, it looks like an even smaller broccoli. This cycle of part equals whole is evident. Fractals are hidden in our bodies too, in the brain and lungs. The alveoli in the lungs are structured to maximize surface area in a limited space for oxygen absorption, and the numerous folds in the brain allow for more neurons. Ferns, snowflakes, lightning, branches, river networks, mountains, clouds, all exhibit fractal patterns. Fractals are considered the fundamental structure of the world because they reveal surprising simplicity and regularity in the seemingly chaotic natural world. Looking at fractals, I thought they were quite paradoxical. Simplicity creates complexity, and within complexity lies simplicity. The small and the large are similar and connected. Finite and infinite coexist. Things that seem contradictory from our perspective might actually be connected as one. Portuguese Nobel laureate José Saramago said about chaos and order, "Chaos is order yet undeciphered."